Good morning, good afternoon.
Hello. Nice to see you guys.
Good afternoon.
Yeah, hi, good afternoon. How are you doing?
Good.
Well, so a reminder that, yeah, good afternoon, who just joined, that this week is we are approaching to the second midterm, will be on Saturday. So all topics which were not included into the first midterm um, until today's topic, gravity. Gravity will not be included. All topics in between, they will be included into this midterm too. So please be aware of that. We will send some reminder later this week by email, but just be aware of this. Actually, it's not 9:40 p.m. If we look into this manual which we shared with you, you will see that the second midterm will be on Saturday from 10 to 11. So we will have this time window from 10 to 11 and 45 minutes. It's actually active midterm time in this time frame. So I believe it should not be any, 10, 11 a.m. in the morning. I think it will not be any, at least should not be any overlap with other exams or midterms, because it should be well organized. So, talking about our discussions now, we are at this stage when we start to discuss gravity, and it's overlapping with HST 100. I don't know what is HST, but if it overlaps with something of history, are you sure? Because the previous section I had the discussion with, they initially also considered that it overlaps with history, but they figure out that history starts at 12 and our exam ends at 11. So you have one, yeah, you see, it starts at 12. So you have 1 hour gap, which is quite okay. Definitely not overlapping. Okay, no problems. It just need to figure this out because it's important. You definitely should not have real overlap, but if it doesn't overlap, everything is fine. So until this time in our previous discussions and along the course, we introduced kinematics and dynamics of translational motion. Later, we did it for rotational motion of rigid objects, also from kinematic and dynamic point of views. However, we still don't have the general picture and understanding of such a fundamental interaction as gravitational interaction and gravitational force is quite essential step. So it is obvious that there is certain force which keeps our moon like Earth's satellite to orbit around it, almost perfectly circular orbit. Otherwise, if there is no any force, according to first law of motion, it would just fly away in a straight trajectory with constant speed. However, it stays around Earth. It is not so trivial to realize that actually the force which keeps the moon orbiting Earth is the same, the force of the same nature which causes the apple to fall down and hit Newton's head, according to the legend. I'm not sure that it was the trigger for a great invention, but it's believed to be like that. So the fact that he and like other scientists of that time, without this like very limited understanding of nature, like physics of nature, at the early stage of physics as a science, came to this conclusion, that's quite remarkable achievement, because it's definitely not so straightforward. But it's indeed true. So there is the same nature, and gravitational force acts on big, small particles with like different masses, doesn't matter what. So we will start our discussion with introduction of this famous equation, which describes quantitatively gravitational force, which interaction between two bodies, without derivation. First, how it was originally published by Newton. Afterwards, we will introduce three laws, like Kepler's laws, which are based purely on empirical observations with naked eye, by the way, without any optical instruments. And afterwards, we will come back to this equation, and based on summarized observations of empirical observations by Kepler in his three laws, we will derive the gravitational, the equation for gravitational force. And we'll show that actually it's enough accurate information we get from Kepler's laws in order to derive this fundamental equation, which describes interaction of any bodies in the universe between each other via the gravitational force. Okay, so let's see what we can manage to do during today's discussion. And obviously what we will not do today, we will finish on Wednesday. But let us start. So the equation, which was published originally by Newton, tells us that gravitational force is proportional to the masses of two particles which interact with each other, m1, m2, and reversely proportional to the square of distance between these two particles. So here is some constant g, which is called gravitational constant or universal gravitational constant. So its numerical value is 667 4 times 10 to minus 11, and units Newton meter square divided by kilogram square. So it was later determined in high accuracy. And this is valid for any any two bodies, regardless of their shape, size, type of material they are made of. This interaction is valid. Also, we can extrapolate this type of this equation towards more familiar situation to us, means how planet Earth acts via gravitational force on bodies, different bodies on its surface. Then we can write that this gravitational force is equal to G times mass of Earth times mass of an object on its surface divided by the radius of Earth. And in this case, it's considered that the mass of the planet is concentrated in the center of mass, which is like the center of the planet itself. So that's why we consider this distance, which is equal to the radius of the planet. So that is from other side. We also know that the because of interaction via the gravitational force, bodies possess some weight. So we can write here that this is equal to m times g, which is acceleration of free fall. And from here, we can express that g is equal to gravitational constant times mass of the Earth divided by its radius squared. So we see that acceleration of free fall is not a constant, changes and from planet to planet, because we have properties which are defined by the planet, which is mass of the planet and radius. So in our case, it's Earth, but it could be any other planet. So what also we need to mention that once we start to go away from the surface of the Earth, there are some changes also in this acceleration of free fall. Let us show this. So gravitational force, we know that it's reversely proportional to the distance between the objects. So we can write mass of the Earth times mass of the object divided by r squared. And this r squared, when we start to move away from the surface of the Earth, can be given as follows. Will be radius of the Earth plus some height h, and this all in second power. So that will be equal to mass of the object, which is constant, doesn't change, times maybe this, times acceleration of free fall at given height. So now we can express that acceleration of free fall at given height is equal to gravitational constant times mass of the planet divided by r radius of the planet plus h squared. So we see that it's not only a function of properties which define mass and size of the planet, but also position with respect to the surface of the planet. So obviously, when we increase this height h, we reduce the acceleration of free fall. So it becomes smaller because h is located in the denominator in this equation. So if we, for instance, if this height approaches infinity, so when the object leaves the planet and lies far away, acceleration of free fall approaches 0. So if, for instance, we will take some example and consider our International Space Station, it's orbiting about Earth at the height of around 350 kilometers. And if we calculate the acceleration of free fall at this height, we will realize that it actually not so much of difference from its value on the surface of the Earth. So it will be something 8.82 meters per second squared. So it's noticeably smaller. However, it's quite big. These conditions which astronauts experience on the International Station, that's only because of continuous free falling of the International Station. I guess I mentioned about this a bit earlier, not because the strength of the gravitational field, which is, we call it acceleration of free fall, G, is so weak there. It's quite high, and without free falling condition, we would weigh almost the same as we do on the surface of the planet. So now we can introduce Kepler's laws, and which actually describe motion of planets. It's necessary to highlight that this result, these like 3 laws, they didn't come obvious for quite a long of times, and it required a lot of efforts and time. So it is based purely on astronomical observations with naked eye of planets moving with respect to the frame of about 700, like more than 700 stars, which could be considered as some reference points when planets are moving about like around these stars. And it took 16 years to develop the mathematical model based on the observations. So it's quite an impressive work done, and a very important contribution. Technically, that led Newton and allowed him to derive this equation for the gravitational force later. So first, Kepler's law states that all planets move in elliptical orbits with the sun at one focus of this ellipse. So let's say we have some elliptic trajectory. So one of the main parameter of ellipse is this so-called semi-major axis A. And also we have 2 focus points of ellipse. So the distance from focus to the center of ellipse is some c. And there is a coefficient which defines how much given trajectory deviates from circular trajectory, like let's say given shape, elliptic shape deviates from a circular shape. So there is eccentric of ellipse, which is E equal to c, distance from the one of focus to the center of the ellipse, divided by the major semi-major axis, A. So if this parameter eccentricity of the ellipse is equal to 0, then what does it mean? It means that focus is located in the center here, like both focuses, because they are symmetric with respect to the center. That means C is equal to 0, so it's located in the center, and we have a circle. So a circle is some particular specific case of ellipsoid, of ellipse. Ellipsoid is three-dimensional shape. It's more equivalent to sphere. So what first Kepler's law states that in one of the focus of this ellipse should be located the sun, and orbit of the planet which moves about this sun will be always some ellipse shape with more or less eccentricity, but it will be an ellipse. So that is first statement, which should be taken into account. Then second Kepler's law tells us already more quantitative information, that the radius vector, so here is the radius vector between the sun and the planet. So let's call it P planet. So the radius vector drawn from the sun to the planet sweeps out equal areas in equal time intervals. So it means that if we consider this radius vector, which gives, like, defines position of the planet with respect to the sun. So obviously it will change because this planet is moving. Then the area which is swept by this radius for each equal interval of time, let's call it dt, will be the same. So that was observed experimentally and stated in the second law of Kepler, Kepler's law. And now let us figure out why it's going on like this. There should be some reason for that. So going a little bit before ahead, it actually some form of statement for the some consequence of the angular momentum conservation in isolated system. We know that sun and a planet could be considered as isolated systems, so we can ignore external forces exerted on this system because they are very weak in comparison to the gravitational force between sun and the planet. So we consider it as a closed isolated system. In that case, let us draw another ellipse. Here is our sun. Then somewhere here is our planet, which is moving along this elliptic trajectory. Here will be velocity vector of this planet. Here will be the, let's write differently, gravitational force, F gravity. we know that, so in this case, this gravitational force will be internal force for this system. And it is always along radius vector r between the sun and the planet E. So it doesn't create any torque on the planet and cannot change the moment of inertia. And taking into account that this system is closed, like isolated, we also can write the following. So we remember that net torque, external torque, exerted on the object will be equal to the rate of changing the angular momentum. First derivative of angular momentum over time. In isolated system, external torque is equal to 0. And that means that this derivative dl over dt is also equal to 0. Means that the angular momentum is constant. So that we keep in mind. And let us maybe go to another slide so we have more space. We can write also from previous discussions. We know that angular momentum is defined as radius vector times linear momentum vector p. So that could be written as mass of the planet times vector product of position vector times velocity vector. So let us take this in this square parenthesis better. So we can define that MP is just a scalar number in front of this product of two vector products. So now we want to deal with the area which is swept by the radius vector per some time interval. So again, we draw this ellipse trajectory. Here is our focus where the sun is located. Let's assume that this is some initial position of the planet. Here we have radius vector r, and it moves over some time to a new position, some time dt, time interval. So here is new position, and this will be dr vector. So change of the position vector. So the area which is swept by the position vector, this one, it will be half of the vector product of r and dr. Because vector product of r and dr will give us the area of the parallelogram, which is formed by these vectors. But the area swept by the radius will be half of this parallelogram area. And that's why we can write that this small area dA swept by the radius vector over small interval time dt will be equal to 1/2 of vector product r times dr vector. And that we can keep in absolute value because area is yeah, always like positive quantity. So now let us write dr, how we can define dr. So dr, change of the position vector, can be expressed in terms of velocity vector, like linear velocity vector, times dt, this time interval along which this change of the position vector dr happens. So now if we substitute it here, it will be 1/2 of radius vector times velocity vector times dt. We see here that this is product of radius vector and velocity vector, which is also here for angular momentum vector definition. So we can use now angular momentum and express dA in terms of angular momentum. dA will be equal to, so we can write here 1/2 of R times V dt, and that will be equal to L, angular momentum, divided, so like absolute value, divided by 2. So absolute value, we don't need this for area as a vector defined. It will be angular momentum divided by 2mp, mass of the planet, times dt. So we just take into account this equation. So if we put angular momentum in the numerator here, then we need to divide, since here we don't have mass of the planet, and here we need to divide it by mass of the planet, and here we have this dt, so we add it here, dt. So it will be L over 2mp times dt. Now, let us rearrange this in a bit different form, where will be dA over dt is equal to L over 2mp. So we see here that angular momentum is constant because sun planet is an isolated system. And also we have mass of the planet, which is also constant. Doesn't change over time. So the rate how this area changes, area swept by the radius vector, position vector of the planet with respect to the sun over time will be equal to some constant. Means that during equal intervals of time, equal area will be swept out by the radius vector. And that is the statement of the Kepler's second law. So with this, we can proceed to the third Kepler's law, and it also more like quantitative with in comparison to the first one. So it states that the square of the orbital period, so we have some period t, means the time for during which the which takes for the planet to make the full circle, full rotation about the sun. So the square of this period, t squared, is proportional to the cube of the semi-major axis. So it will be a cube. And the reason for this is actually the consequence of angular momentum. Actually, no, that's for the second Kepler's law. But like let's consider a circular orbit in order to show why do we have this relationship. So why we consider circular orbit? Because it will be just easier to show the relationship. Keep in mind, if E, this eccentric coefficient, is equal to 0, then radius of the circle is equal to semi-major axis of ellipse A. So it's some particular case of ellipse circle, and it's just easier to do the math in order to show this proportionality. So since now, when we operate with radius, it's valid not only for the radius of the circular trajectory, but also valid for their semi-major axis. So let us consider a circular trajectory. Here, let us put the mass of the sun. And here is our planet, MP. So it possesses some linear velocity vector and radius r. We know that in order to keep this system going like this, there should be a balance between two forces. So first we have, from one hand, we have gravitational force, which attracts this planet to the sun. So F gravitational. And from other side, we have centrifugal force, which is equal to mass of the planet times centripetal acceleration. And they need to counterbalance each other. So we know expression for gravitational force. It is gravitational constant times mass of the sun times mass of the planet divided by distance, radius r, and that is equal to mass of the planet, and centripetal acceleration can be given as v squared divided by radius of this circular motion. So now we can already cancel out these guys, mass of the planet, also radius here and square here. So since we need to deal not with the linear velocity vector, like linear velocity, but with the period t, so we need to express linear velocity in terms of period. So any ideas, guys, how we do that? V is equal we remember that is equal to angular velocity times radius. Yes? And how we can express angular velocity in terms of period?
Angular velocity is 2 pi over t.
Yes, exactly. Thank you. 2 pi over t times radius r. So that will be our linear velocity. So once we have it, we can substitute it here. So it will be g times mass of the sun divided by r will be equal to v squared. It will be 4 pi squared divided by t squared times r squared. So now we can express t squared. So it will be t squared is equal to 4 pi squared divided by g times ms. And here will be r cubed. So this quantity in parentheses, it's a constant because we have 4 pi. G is universal gravity constant, and mass of the sun also doesn't change. So we can write, let's assume that will be some k, some constant k times r cubed. We see that t squared is proportional to r cubed. So taking into account that r can be substituted with a, we can also, for elliptic trajectory, sorry, we can also write that t squared is proportional to a cubed, which is the statement of the third Kepler's law. Yes, exactly, Kepler's third law. So we went through all these Kepler's laws, explained where they originate from. However, keep in mind that Kepler didn't know the explanation of these laws. He just stated in these laws what he and his colleagues observed during many years of observations and analysis. But that definitely makes sense, and his conclusions were obviously correct because it's in correlation with our nowadays understanding of the physics of nature. Moreover, this, as I mentioned earlier, this empirical results summarized in 3 Kepler's laws will be actually later used by Newton to derive this equation for gravity force, and that we will go through during our next discussion on Wednesday. So we will see how we can get the equation for the gravity law. Would you please repeat what is E? Yeah, E is eccentric coefficient, or eccentric eccentricity of an ellipse, and it is equal to C divided by A, where C stays for the distance between the center of the ellipse to its one of its focus. So this is ellipse. So here we have focus two focus. This is C, and A is semi-major axis of the ellipse. So if C is equal to 0, then both focuses are in the center, and E is equal to 0. Consequently, that is valid for a circle. I mean, for the shape of the eccentric on motor, yeah, sure. We deal not only with shapes, elliptic shapes in trajectories of planets, but they are also used in some mechanical engineering, and definitely obviously that also follows applicable these concepts to other cases, not only motion of planets about sun. And yeah, if E is not equal to 0, then means we have not a circle, we have an ellipse, because that automatically means that the focuses of ellipse are not located in the center. They kind of deviate from the center, means that this elongation of the circle in the direction of this semi-major axis becomes more and more. So we go with E, a larger E, we go to more elliptic shape, which is kind of stretched along the direction of the semi-major axis of ellipse. Okay, guys, thank you very much for attention. We will continue this discussion on Wednesday when we meet next time. Take care and see you on Wednesday. Bye-bye. Have a good day.
Thank you very much. Bye.
Bye.
Thank you for the informative lecture. Goodbye.
Mhm.
Thank you. Goodbye.
Bye-bye.